Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 24. We're doing the negative binomial. Last time, we introduced the negative binomial distribution. If you recall, the negative binomial is the distribution of trying to get R successes. So we keep repeating these independent Bernoulli trials until we get the rth success. Now, this is a generalization of the geometric distribution where we were waiting until we got the first success. So we kept repeating the trial until we got the first success. So R is equal to 1, that's a geometric. R is greater than 1, well, R is equal to 1 is also a negative binomial. But in the negative binomial, we can have R greater than 1. We also went over how to get the MGF. I gave you the derivation in the video. I didn't go over it, but I hope that you will look at that and make sure that you know and understand how we manipulated the exponents. That is a good technique to have, and you might need it later on in the course. If you have questions, by all means ask me, and I will be glad to go over that. We also went through the derivations for the mean and the variance, but very briefly. I didn't get into the details. It's a lot of algebra, a lot of manipulation there. But we did give the formula for the mean and the variance. This time we're going to talk about examples. So we're going to use what we learned and do some actual examples. So let's say we have a basketball player, and during practice this person can make 80% of their free throws. Okay, so 80% success rate. Right here we're talking that P is equal to 0.8. So that means that Q is equal to 0.2. Assume that these are a sequence of independent Bernoulli trials, that him shooting free throws are independent Bernoulli trials. Let X be the minimum number of free throws required in order for the player to make a total of 10 shots. Making the shot means it's a success, right? Okay. So we plug in and get the PMF. That's the first step, is always write down your PMF. And remember to include the range of X, or the support of X, in your answer. And I should have simplified this to 9. So please do that. I shouldn't have left it like this. I apologize. I like to leave this in the form that I want you to do. To the 10.2 to the X minus 10. And then we definitely need X. All right. So we plugged in for R as 10, minus 1 is 9. P is 0.8 raised to the R, 10. Q is 0.2 raised to the X minus R. We want to first find mu. So mu is E of X, and it's equal to R over P. Now, always write down your formula, then fill it in. And if you want to get full credit, do that, please. And so I plug in for R and P, and we get 12.5. Now notice that this is in the range of X, and it should be. Remember that the mean is the expected value of X, so the expected value of X should be a value that X can take. If it's not, there's a mistake. You may have written the formula wrong, you may have plugged into the formula wrong, you may have hit the bad key on your calculator, something went wrong. So now let's find sigma. Now I'm going to start with sigma squared. I like to take the square root at the end, but you could start with the square root, of course, if you like. And again, I write down the formula so I don't make a mistake. Even as experienced as we all are in this class, it's easy to make a mistake, especially on a test or when you're rushing. So it's always better to write down the formula and make sure you plug in, and it's going to prevent a lot of mistakes for many of you. So I plug in, I get 2 over 0.8 squared, which gives me 3.125. Remember, don't round until you get to the end. So that whole thing goes into the square root, and then we round, and I didn't say how many decimal places, so I did it to 4 decimal places in this case. The problem should tell you for sigma and for mu. If there's rounding needed, we should specify it. Okay? If not, ask, and I'll be glad to tell you. P of x equals 12. So what's the probability that this basketball player needed to make 12 shots to get 10 of them in? And so we plug in 12 for x, and so 12 minus 1, the 10 was for r, the 12 was for x, and so we plug in 12 again here, and we end up with 11 choose 9, 0.8 to the 10, 0.2 squared, and this turns out to be 0.2362. Now on probabilities, I want you to round to 4 decimal places unless it says otherwise. Now let's take a look at some of the shapes of the negative binomial. What's going on here? How's it changing? So this is the geometric distribution. R is equal to 1, and we have P is equal to 0.25. And you'll notice that it's skewed right, but it's extreme. I mean, there is no hump. It just like it goes up to infinity there, right? We move to R equals 4, and we change P to 0.6, and we get a skewed to the right distribution. Sometimes I'm not really sure why the author doesn't do some of the other distributions. I would have been interested in, since these are all above 0.5, I would have been interested in something besides R1 that was less than 0.5, but this is what they show. And then we'll see that in all of them, we really have the skewed to the right distribution. And look at how, so P has changed to 0.7 here, and it's staying at 0.7. When I increase R, look what happens. It flattens out. It gets thicker and flatter, okay? So as R gets smaller, this gets more peaked. So 0.6 to 0.7 is not is a change, but you can see from R is 4, but we're having two things change. R goes from 4 to 7, and it looks like the peak gets bigger. And if we keep R, we keep 0.7, the P the same, and we increase R, it gets thicker and smaller. So yes, so as we decrease R, this gets thinner. The distribution gets thinner. As we, looks like as we increase P, we change the skew, okay? So we're changing the shape. All right, so here's what they look like. Hopefully that gives you an idea of what happens there. Now, let's talk about this remark. When the moment generating function exists, the derivatives of all orders also exist at t equals 0. You say, well, if I have mgf equals to, or m of t is equal to x squared, well, I can only take two derivatives. That's not true. So mt is 2x, m prime t is 2, m3 of t, I'm just going to leave it as t, equals 0. So is m4, the fifth derivative, sixth derivative. You can still take them. It's 0. But you can take as many as you want. So they do all exist. This doesn't say whether or not they're 0. Okay. So when I first saw that, I questioned it many years ago, and so I wanted to point that out to you. Okay. So we can, it's possible then to represent this as a Maclaurin series. So we've got mt, and so m of 0, m prime of 0, and then t over 1 factorial. And so you can see the pattern of the Maclaurin series. If this exists and the moments are given, it's often that we can write this in a closed form. So m of t can be written in a closed form. Notice I say often, not always. So here's an example of this. We're going to let the moments of x be defined as e of x to the r is 0.8. So that means it's a constant. And that's for r equals 1, 2, 3, etc. All right. And we can then write mt, and I guess I should write r as 0 as well. All right. So we can write this as m0 plus the sum from r equals 1 to infinity. Notice that 0.8 is our moment here. And then t to the r over 0.8. All right, so what we're saying is that the derivative, when we say e of x to the r, that's mrt. So all the derivatives are 0.8, so they're constant. Okay, so an interesting looking MGF there. All right, and we have this sum, and so we put in t to the r over r factorial. And remember that m of 0 is always 1. Always 1, yeah, so that's why this is not 0 included there. So we've got always 1. 0.8 can come out to the front as a constant. And then we have r from 1 to infinity, t raised to the r over r factorial. And so I'd like to point out to you that then we need to make this as from r equals 0 to infinity. And so what we've done is we have broken this 1 into 0.8 plus 0.2. Because we already had a 0.8 here, we decided that we needed another 0.8, and that would be, so our sum needs to be, when r is 0, it needs to be a 0.8. So this quantity needs to be 1. And when r is 0, we have t to the 0 over 0 factorial. So it is in fact 1. And we have a 0.8. And then the 0.2 stays out here. And so now we can take this and say that r is equal to 0. And we can write this as 0.2 e to the 0t, because that's 1, plus 0.8 e to the 1t, because this quantity here, you should remember from algebra that it is a way of writing the natural number e. And so we have just recreated the moment generating function. And so we have p of x equals 0. If you plug in, that's 0.2. Right? And when x is equal to 1, we have 0.8. And this is e to the t, which is the same thing as e to the 1t, isn't it? Okay? So this is a Bernoulli distribution. Oops. Sometimes having a little trouble with my iPad. All right. So that's a Bernoulli distribution. Okay. So those are our examples for this time, and that's a nice property to have. So don't forget to scan in and upload your lecture notes before midnight on the date listed in the course calendar. Make them neat, of course, for you. You'll want to update your list of distributions, probably your formula sheet or list of facts or whatever it is that you want there, and your theorems with the remark here about the moment generating function. And if you have any questions, please come to virtual office hours. If you can't make those and you have a question, by all means, email me, take a picture of the problem, take a picture of your work. If you do that, then I'll be able to help you by email. Of course, if we can meet, if both of our schedules allow us to meet, then we can do that as well if you like. So you take care, and we'll see you next time.